Thank you very much for the introduction and for inviting me to this conference. So I have to apologize a little bit that there will not be any optimal transport at this talk, but there will be Calabi-Yau, so I think it's okay. Okay, so in this talk, we're going to mainly work in C2, but I mean, many of the things are more interesting if you work in a compact Calabi-Yau. Depending on your comfort level, you can imagine everything is in C2 or compact Calabi-Yau surface X. So that's the deal. So like a K3 surface. And everything can be done in higher dimensions too. It's just that we know much less. So the nice results are really in dimension 2. Okay, so let me introduce some of the notation. Okay, so this omega is going to be the standard symplectic form on C2. Okay, or on the Calabi-Yau, it will be the Kähler form. And then this big omega is the holomorphic volume form. And then this talk, factors of 2 are all equal to 1. So everything is modulo factors of 2. Okay, and then we're going to study Lagrangian surfaces. So if you have a 2-dimensional real submanifold of this C2 or X, then this is called Lagrangian. If you take this symplectic form and you restrict it to L, then it just vanishes. Okay, so then there's this notion of being graded. Okay, there's such a Lagrangian is called graded if there exists some so-called angle function. So this theta should be, so I call the Lagrangian angle, the real valued function, such that if you take this holomorphic volume form, if you restrict it to L, then this will be some complex top-dimensional form on L, like a complex 2 form on L. And then you can also compare it to the volume form on L, which is another 2 forms. Let's say L should be oriented. So you have a natural area form from it just being a nice submanifold of C2. It turns out that being Lagrangian is equivalent to saying that this holomorphic volume form restricted to L is at each point a unit complex number times the Riemannian area form. Being graded means that you can actually define a kind of global phase function. So that you have this formula. And then, of course, this theta locally is always defined up to adding 2 pi. And then this graded means that you can kind of globally define it, where there's usually some topological obstruction. Okay, and then there's a very nice fact which underlies a lot of the connection of this special Lagrangian geometry to like minimal surfaces, namely that if you take this theta, then you can take its gradient on L. This will be some a vector field tangent to L, and then you can take this J of this vector field, where J is the complex structure on C2. So it turns out that this vector field will be normal to L, and the basic identity, which you can spend the rest of this lecture deriving if you want a nice exercise, this is equal to the mean curvature. Okay, and this uses the Calabi-Yau condition. So okay, on C2, it's not difficult to verify this, but in general, this is basically true if you have a Calabi-Yau manifold. So there's this connection between the Lagrangian geometry, the complex structure, and the kind of extrinsic Riemannian geometry. Okay, and then L is called special Lagrangian. I usually just write SL if this angle function is constant. And then because of this formula, that's basically the same as saying that the L is a minimal submanifold as well as being Lagrangian. Okay, so special Lagrangians are just minimal Lagrangians. Okay, and then I need to do just one more thing. So L is called exact if I'll write down what this lambda is. So there's this Liouville one form lambda. Exact means that lambda restricted to L is an exact form. Okay, so this lambda, I mean, again, also on C2, this is some specific form. So it's just the sum of, let's get the sign right, xi dy minus yi dxi. And the point of this form is just that d lambda is 2 times omega. Okay, so if you have a Lagrangian, then d lambda restricted to L is 0 because it's omega. Okay, so lambda is always a closed form on a Lagrangian, and then exact means that it's an exact one form. Okay, and then you might already worry that in your other setting, this doesn't make any sense because in the compact Calabi-Yau case, you could never find such a lambda, like the omega would not be an exact 2 form. Okay, so in that case, you have to do something a little bit different, which I'm not going to explain. But so this exactness really just makes sense on C2 or so-called exact simplex, like exact Calabi-Yaus, which would be non-compact. But there's a similar thing called rational, which I don't want to go into. It's a good replacement for exact. Okay, so throughout this talk, everything will be either in C2, we only care about graded Lagrangians, which are exact, or in a Calabi-Yau, we care about graded Lagrangians that are rational, whatever that means. Okay, so the topic of this talk is the Thomas-Yau-Joyce conjecture. Okay, so like in the late 90s, Thomas and Yau were motivated by mirror symmetry. They were looking at how you can relate a Lagrangian in a Calabi-Yau manifold to a special Lagrangian. So if you know about this kind of stability and Kähler-Einstein, Kobayashi-Hitchin correspondence type results, by mirror symmetry, there should be some analogous statement saying that if you have a Lagrangian, and if it's stable in some sense, then you can somehow deform it to a special Lagrangian. Okay, so Thomas and Yau, I guess maybe Thomas had an earlier conjecture relating these two pictures, and then with Yau, they realized that the mean curvature flow is a very natural way to approach this problem. And basically, they made a conjecture saying that if L is stable, and they made some condition of stuff, they wrote down some condition, which I don't want to spend time on here. So under some sort of stability condition, they conjectured that any Lagrangian will flow along the mean curvature flow to a special Lagrangian. I mean, sorry, if it's stable, like any stable Lagrangian can be deformed. Okay, so it turned out that their stability condition, well, it somehow didn't seem that natural. It seemed to be it works in some cases, but somehow there seemed to be a bigger picture behind it. So then Joyce made this very ambitious program relating this whole thing to bridge length stability conditions through mirror symmetry. And then, okay, this is starting to be way above my competence. So in the end, I'm going to state a very informal version of this for people who like kind of down to earth things. Okay, so the basic maybe we can summarize this whole program as saying that if you take any initial Lagrangian, could work in C2 or in the Calabi-Yau. If this is Lagrangian, the mean curvature flow okay, so the mean curvature flow is just this evolution equation where you evolve submanifolds in the direction of their mean curvature. So let me write it like this. So this mean curvature flow should decompose this L0 into special Lagrangians. And then really what you need is some kind of flow with surgeries so that it needs to allow the Lagrangian to break up into pieces at various times. And then what you should imagine is that in the end, like, okay, say you start with a Lagrangian sphere, and then in an ideal situation, there will be certain times at which the sphere breaks up into more spheres. And then eventually all these different spheres flow to special Lagrangians in the limit. And the key aspect is that these special Lagrangians still have a phase, this theta, and then this decomposition, you could have, the pieces could have different phases. Okay, so again, if you're familiar with, like, say, like stable vector bundles and that kind of subject, then this would be some sort of analogous decomposition to the Harder-Narasimhan filtration, where you can take any vector bundle and then you get some sort of filtration of it such that these consecutive quotients are stable with perhaps different like slopes. Okay, so there's, anyway, it's too long to explain all of this thing. So if you're not familiar with that, then it's enough to just think of this as a kind of natural thing. Like Lagrangians are very natural objects. Special Lagrangians are very special. And actually, they're very hard to find. So there are very few constructions that tell you, like, there are some perturbative methods with gluing and things like that, but there are very few existence results. Okay, so this somehow would be a kind of very general existence statement, and it would somehow say that any Lagrangian is somehow built up out of special Lagrangians. Okay, and that's deliberately very vague because we're so far from being able to do anything like this that it doesn't really make sense to like make some big, like precise conjecture. Yes?
Is there anything about uniqueness?
Oh yeah, so there are nice uniqueness results. Okay, so at some point, the story to understand it more deeply needs the Fukaya category. And then the correct statement would be that in this derived Fukaya category, each object can be decomposed into stable objects, and then the stable objects would be represented by some kind of unique special Lagrangian. So, for example, you cannot have two special Lagrangians that give you the same object in the derived Fukaya category. So the baby case of that is this very beautiful uniqueness result of Thomas and Yau, which says that if you have two special Lagrangians, then they cannot be Hamiltonian isotopic to each other. So then and a kind of more like fancy version of this is this Fukaya category statement. Okay. So then so in the rest of the talk, we basically want to study this question and mainly just from a kind of analytic point of view. So what would we need to do to like make some progress on this conjecture? Okay, so the basic issue is that singularities can form, and in fact, we want them to form because we want some sort of decomposition to happen. So we need to understand like how to study singularities. Okay, singularities can form. And then we study these using this idea of a tangent flow. Using tangent flows. Okay, so let me just write down the definition of a tangent flow. So, okay, suppose that you shift time, so you can change it, shift time by some negative number if you want, and shift in space so that the singularity occurs at time 0 at the origin. Okay, so let's suppose you have some singularity at t equals 0 at the origin. Okay, you can always translate your flow to make this happen. Then we consider these rescalings. Okay, so for any, say, positive lambda, you can make this new flow, which is lambda times L, then lambda to the -2t. So this is the correct parabolic scaling, so that for each lambda, this also satisfies mean curvature flow. And then what you do is you just take a limit, let's call it like L infinity t. As lambda goes to infinity, and okay, as you probably the experts know, there's this question of, different sequences may a priori lead to different limits, but let me ignore that here. So any limit you extract in this way is called a tangent flow at this singularity. And then for later use, let me just say that it's kind of convenient to define this so-called rescaled mean curvature flow. Which somehow just does this rescaling in a kind of continuous way, and you change the time variable to some sort of logarithmic time, and then, so I write it like this. So m tau is going to be e to the tau over 2, and then L minus e to the minus tau. So basically, it just changes variables, and you see as tau increases, then this negative number goes to 0, and at the same time, you're kind of blowing up the flow. So in the limit, what this will be is basically the same thing as the time -1 slice of this flow. I can write it like this. It's a kind of continuous rescaling process that makes it much easier to study tangent flows. Okay, so if you study mean curvature flow, then you know that these tangent flows are always these so-called shrinking solitons. So this blow-up procedure generates this kind of invariance. And then, so that corresponds to the fact that this rescaled flow should converge to a so-called self-shrinking solution of the flow as tau goes to infinity. Okay, so if you like real mean curvature flow, but you've never seen this Lagrangian case, then I think this result is very interesting, that in the Lagrangian case, any tangent flow is always, in this two-dimensional case, it's always just a union of planes. This is in this 2D case, or in the Calabi-Yau surface. So it's going to be a union of Lagrangian planes. Okay, so as a static flow, or you can think so this m tau will converge somehow to a union of planes. And okay, there are several difficulties that, so as soon as you have two planes, so the planes through the origin. So as soon as you have two planes, you'll have a singularity at the origin. So kind of traditional techniques from mean curvature flow don't work so well because you can't write the flow as a graph near that point. And you can also have things like multiplicity. So anyway, there's lots of difficulties. Multiplicity is possible. Okay, but at the same time, at least it's always just planes. So whereas in regular mean curvature flow, you can have many different singularity models, but they're not possible to classify. Okay, so in this talk, we're going to focus on the two simplest options.
These two planes have, these two planes are independent, or
Sorry.
These two planes have some angles, or
oh yeah, so they could have different angles. Yeah.
okay. Not fixed angle.
Yeah. So you could so that these two cases will be one of them is what you're asking. Okay, so
The arbitrary angle.
yep, it can be. Okay, so the very simplest case is when it's just one plane, in which case there's no singularity. Okay, so the next simplest case is two planes, and then there are two options. One which is called the neck pinch. So this is when the tangent flow is a special Lagrangian union of two planes. So this means that the two angles are the same of the two planes. And let's say two transverse planes. Okay, I'm going to, from now on, what I'll write as like P1 union and then 0, P2. Okay, so they meet only at 0. Okay, and then a result that I proved with Jason Lotte and Felix Schulze. So a few years ago, we proved that if this is the tangent flow, then actually geometrically, what the flow does is it really breaks the Lagrangian into pieces. Like it's really kind of a neck pinch. So you can say, okay, I'll be a little bit vague, but in a quite precise sense, you can say that the singularity is modeled on this family of complex curves. Okay, and I'm using this different letter because, so these are not the complex coordinates from the beginning, because complex subvarieties cannot be Lagrangian. Okay, so what it turns out that in this dimension, you can choose different complex structures, and then with respect to a different one, you can write the flow like this. Okay, so this is really these like hyperbolas in the limit converging to two planes, and you have some kind of vanishing sphere that's like the neck being pinched.
This union 0 means what?
So the epsilon going to 0 is that that the neck.
These two planes, 0.
Sorry.
Sub-0 in the union.
In the next case, we'll have a line here. So later when I write this, just to remind you that this means two transverse planes only meeting at the origin. Okay, and then the picture literally is that you have some sort of like picture like this, like a surface with some sort of neck. And then as epsilon goes to 0, or as in along our flow, as you approach a singular time, then in the limit, okay, I don't know how to draw two transverse planes. But then what you can do is at this point, you can flow, like now it's an immersed Lagrangian, and you can flow the two separate pieces like separately. So you can continue the flow as an immersed Lagrangian. So you could imagine that now these, at least locally, these two pieces can keep evolving, and you still have this intersection. So the picture you should have in mind is that if you start with a two-sphere and you do this to it, then now you'll have two spheres. And then this is the basic mechanism for breaking up into many pieces.
The model already, testing it.
Yeah, that's right. That's true. Yeah, so this is, yeah, I guess we'll get to that in a bit. So yes, so one of the difficulties is that this is the so-called type 2 singularity. So to leading order, it already looks static, like the surfaces for fixed epsilon modeled on this would not evolve along the flow. But there's like a next order correction which forces the neck to pinch. So this, if we only ever saw these singularities, then we would be done. Like then this thing would break up the surface into pieces, and then okay, maybe modulo some technicalities as t goes to infinity, you would expect that each piece would become special Lagrangian. Yes.
You see, so you said you see the transverse planes, and there's a next order correction that forces. Say a bit more.
I will later. Okay, and then the other type of singularity is what? So I call this teardrop. So if you have a problem with this, then make better suggestions for the name. I feel like it has to have some name. Okay, so here, this is the case when you have, again, two planes, but it's not a special Lagrangian union. And so, okay, there are two cases. You could have two planes meeting at the origin with different angles. It turns out that that's not possible. So Neves ruled that out already. So then the remaining possibility is two planes meeting along a line. Okay, so the tangent flow. Two planes meeting along a line. And then necessarily you can check that then that the two Lagrangian angles will be different. Okay, so here, this, because they're different, this means that this is a non-special Lagrangian tangent flow. And what that means is that we would expect that if you encountered such a singularity, then you should not be able to continue the flow as graded Lagrangians, like something bad happened to the Lagrangian angle. It has some sort of discontinuity because you had these different pieces with different angles collapsing to a point. Okay, so I don't know if there's a theorem about this, but anyway, likely the flow cannot continue as graded Lagrangians. Cannot keep flowing. And the reason why we like graded Lagrangians is this connection to this Fukaya category. So if it's not graded, then somehow that part doesn't make sense. So it's natural to expect that we only care about graded Lagrangians. Okay, so here I can, you can also do mean curvature flow in C for curves. So any curve is Lagrangian. And then you've seen curve shortening flow, you've seen that if you have some sort of loop like this or a teardrop, then you can, at some point, you'll have some singularity like this, some kind of cusp. And then the flow will smooth this out. So you can keep flowing as a curve shortening flow. So you'll get something like this. But if you keep track of the grading, which in this case would just be the angle that you make with the x-axis, so this theta is literally just the angle of the tangent vector, then you'll see that somehow something bad happens here. You lose like pi, or yeah, I think about pi of the angle, or 2 pi. No, yes. Anyway, somehow if you keep track, like if this is, say if you make the thing like this, you start with, like if this is angle 0, and then you go around, then this will be angle pi. But if you do it here and you go in with 0, then this will be like minus pi. So like you can't somehow consistently define the grading through this process. Okay, and then the same, yeah, the problem is that here, at this point, the tangent flow is a multiplicity 2 line, but one line has angle 0 and the other line has angle pi. So this is like a non-special Lagrangian tangent flu at this point. Okay, so this second type is very bad. And actually, for a while in this field, people were trying to rule this out. And for example, there's a paper of Neves and Tian where they have various conditions under which they say that, like, to rule out this possibility. But I think, it seemed like nothing seemed to work. And then it was Joyce's conjecture that sort of explained that actually it's okay, maybe this can happen, but then probably you need to go back in time a bit and do some kind of surgery. Like somehow you need to do something earlier, which will prevent the situation from ever happening. And again, this is a little bit more complicated to explain. Okay, so let me just vaguely say what Joyce conjectures in these two cases. Okay, so to deal with this too, what he says is that you should actually equip the LT with some extra data called a bounding cochain. Okay, so this is something that if you know about like Floer homology, then it's like a natural object. But if you don't, basically all it is that if you have an immersed Lagrangian, that at every self-intersection point, you associate some like extra data to it. And then this extra data will evolve as the flow moves. If your LT is embedded, then you could just say that this is just trivial. Okay, it's something that happens once your flow is immersed. So at these points, you would associate, like, say, a number or some point in a vector space or some more complicated object.
If it's
Yeah, exactly. Yeah, a good question. So this bounding cochain BT, which will evolve along the flow. Okay, so yeah, I'll get to your question in a second. But then in this case two, what he conjectures is that the only way for this bad singularity to form is that you have a kind of picture like this. So first of all, this singularity should not happen if the flow is embedded. It should only happen if the flow already became immersed at some earlier time. And then something bad happens to the bounding cochain at that corresponding point like this. And then what his conjecture is that, well, you have this point, you should go back in time to the first instance when this bounding cochain became bad. And then he proposes some surgery construction. So basically, anytime you have an immersed point, you could flow out of this picture in different ways. Like you could, instead of keeping it immersed, you could decide that I want to now flow like this or something. Or you could flow from this one, you could also continue like this. So whenever you have an immersed point, you have some choices to make. And then his proposal is that you find that first time when this bounding cochain became bad, and at that point there is a different choice that you should have chosen instead of just mindlessly flowing this immersed thing. Okay, we are extremely far from being able to like show that this is really the case. But okay, let me say that. So these teardrops can only happen if the flow is immersed. Became immersed. And this DP is bad. I don't know how to explain it. There's some sign that should always be positive, and then at some point it may become zero. That's the bad case. Okay, so let me not write more about that. But then, so because he made this suggestion that you have this extra data that you need to keep tracking, then we better make sure that this extra data behaves well along the neck pinch that we like a lot. So geometrically, this is very nice. But now what will happen is, like we're asking, the flow could become immersed at this point. So now you need to put this bounding cochain at that point, and that bounding cochain cannot become bad instantaneously. And that corresponds to something needs to have a sign as you flow out from this singular time. So, okay, it's just too technical to explain, but it basically boils down to that there needs to be some inequality between the two the two sheets that you see here. As you flow forward, you have to keep track of what happens to the Lagrangian angle at that point on the two different sheets. So let me call this the Joyce angle condition. Okay, so the bounding cochain BT can only be defined after one of these neck pinches. Okay, and this I'll explain a little bit more later. After a neck pinch, if the sort of Joyce angle condition holds. Okay, and then what he conjectured is that you can always arrange that if you see a neck pinch, then maybe after perturbation, this extra condition will also hold. Okay, so maybe let me say what the results are. So the first main results. So first one is to do with this second conjecture. So basically, okay, sorry, all of this is going to be stated a little bit vaguely because it's just too much detail to write down all the assumptions really carefully. Okay, but let's suppose that you have your nice Lagrangian mean curvature flow, and that sometime t, suppose that you're in a situation that this time slice is sufficiently close to this kind of neck pinch model, so that this W1, W2 equals epsilon with epsilon very small. Okay, so what you should imagine is that maybe after rescaling, after making everything very big, this time slice has like a huge piece which looks basically like this hypersurface or this surface. Okay, then the conclusion is that there exists some small perturbation of this LT, so a small Hamiltonian perturbation. Let me call it LT prime of LT, such that this LT prime has a neck pinch, which also satisfies this good condition. Such that if you now start with this new condition, yes, so it's small, but it's not arbitrarily small. Like, so if you, like if this LT is say within delta of this thing, then this perturbation has to be somehow not arbitrarily small compared to delta. So it's like there's this kind of subtlety. I can draw a picture in a second. Okay, so then the flow starting with this perturbation is what I call non-degenerate. Oh, sorry, no, is what it has. It has a non-degenerate neck pinch, which satisfies this Joyce condition. So okay, the takeaway from this is that, so I'll tell you in a second what non-degenerate means, what the definition of that is. But if we only ever saw non-degenerate neck pinches, then this Joyce program with this banding cochain would also work. And then you could keep defining the BT through the singularities. So that would be nice. But actually, already without any of this non-degenerate stuff, a nice consequence of this result is that it gives you the first examples of finite time singularities, where you start with a surface that's arbitrarily close to special Lagrangian. So an example you can do kind of explicitly is that, so this LT, this could actually be a special Lagrangian torus in like an elliptically fibered K3. So basically you take like an elliptically fibered K3 where you change the complex structure so that the complex tori become special Lagrangian. And then if you just go closer and closer to a singular fiber with a nodal singularity, then you'll be exactly in this situation. So if you have some, here you have a singularity in this elliptic or torus fibration. If you take the surface, the tori that are very, very close to this, I don't know how to draw it, then maybe these ones should have more like topology. Okay. So if you go very close to this one, then the point is that in some neighborhood like this, it will look exactly like this model. Okay, so you can apply this theorem to these tori that are sufficiently close to the nodal curve. So in particular, this will give you examples of these finite time singularities, starting with something that's arbitrarily close to special Lagrangian. And what's also interesting is that, well, these guys are already special Lagrangian. So if you actually start with the fiber, the flow doesn't do anything. And then what we're doing here is you take this fiber, you perturb it a little bit, and then a singularity forms. But if the whole Joyce conjecture is correct, then eventually the flow should be getting you back to the original special Lagrangian, because these fibers are already special Lagrangian, and there cannot be any other equivalent special Lagrangian that it should decompose into. So this is what explains this other. So it suggests that you really need this other thing in the Joyce conjecture. You need something like this, that first statement, because once the singularity forms, then something else has to happen that forces you to kind of undo it, to undo this neck pinch to get back to the original torus. Okay, so we don't really understand yet like how that happens, but okay, if the conjecture is true, then it has to happen. Because you cannot, once you do this neck pinch, then the new surface cannot possibly flow to a special Lagrangian. There cannot be any special Lagrangian in that Hamiltonian class. Okay, and then let me just state the theorem to do with these teardrops. So, okay, suppose that this LT develops, and again, this word non-degenerate, which I'll try to explain. It develops not just a teardrop, but a non-degenerate teardrop. Singularity at some point, say T0, T0. Okay, then what we can show is that the flow cannot be embedded near this point. Yes, you should imagine T is less than T0 and close to T0. Okay, and this is the other thing that we need in this Joyce program, that if this teardrop forms, and maybe we need to do some perturbation to achieve this non-degeneracy. But if you have a non-degenerate teardrop, then there had to be an inverse point, and then that's somehow the first step to verifying this prediction of Joyce, like what to do. Okay, so let me explain. So what are these non-degenerate things? Okay, so in the remainder of the talk, I'll just try to explain what is behind these type of results. Okay, so the key point is that this tangent fluid that we defined, that's just a sort of infinitesimal behavior of your fluid. It's like the first order, first order behavior of the fluid. To see non-degeneracy, you need kind of the next term and the sort of Taylor expansion if you want. You need to go to the next level approximation. Okay, so let me just write that down. So the tangent fluid is that's the kind of infinitesimal information about the fluid. It just tells you like the leading order what it looks like. To see this non-degeneracy, you need the next order term. You could think of it as some sort of asymptotics. So remember, I had this rescaled fluid, and having a tangent fluid that just tells you where does this converge as tau goes to infinity. So we had this, I think I wrote this down. So this shrinker, which in our case is like a union of planes, having a tangent fluid, or knowing what the tangent fluid is, just says as tau goes to infinity, then in some kind of measure sense, this fluid tends to this union of planes. And then you could imagine that you have some kind of next order asymptotics, like this plus what is the next term? Okay, so this kind of thing is much easier to do if we had compact, smooth tangent fluids. But anyway, let me just look at this. Again, I'll be somewhat vague, but the real difficulty is somehow making all of this precise. And the difficulty is that this thing is singular and non-compact. So it's not so easy to write everything as like a global graph and then linearize and then compute some sort of formal asymptotic expansion. Okay, so in this case, we have this assumption. So this means that so as tau goes to infinity, we can write this m tau as a graph of some, I guess, vector field over this union of planes over some larger and larger open subset of this union of planes. And then you would expect that this V will go to 0. Maybe an L2 or something. Okay, so because it's Lagrangian, then actually this and exact, everything we're doing is exact. So actually this V you can write as D of a function, or the kind of dual, like the D of a function will give you a one form on this thing. And by using the symplectic structure, you can convert that into a vector field normal to the Lagrangian. So let me just say, you can write V as some D of F. So really you have to identify this with a vector field using the symplectic structure. And then you would linearize the mean curvature flow equation. So what you get is to leading order, this F satisfies this drift heat equation. This equation. So there's some higher order nonlinear effects. Okay, but we would expect that somehow to leading order, the behavior of the flow is determined by solutions of this drift heat equation. And remember, so this is just on P1 union P2. So really this is just, you could think of this as like two drift heat equations on two planes. Okay, so it's like a very classical thing to study solutions of this. Yeah, so if you work out what the condition is, then you can show that actually at the origin. So really what you get is two solutions of the drift heat equation on the two planes. So you can prove that near the origin, you have some removable singularity. And then to leading order, it's literally just governed by a pair of solutions on the two planes.
You have this graph all the way down to the origin or just away from the origin?
Well, it will always just be away from the origin, but then somehow to lead, like you can control how much bad stuff happens near the origin. So somehow in a suitable sense, the leading order behavior is still governed by these solutions on the whole two planes. Okay, and then since the V goes to 0, then you would expect these Fs to also decay. So if you know the theory of these equations, you would know that, okay, there's a solution that's like e to the tau, like times a constant. Okay, that one grows, moreover, it's constant anyway, so it's kind of irrelevant. Then the next solution is like e to the tau over 2 times some linear functions. Okay, those blow up as tau goes to infinity, so you shouldn't see them. Now the next order will be some quadratic functions, basically like x squared minus 2 would be the one-dimensional version, and those are static in t, or in tau. Okay, so that one does not decay, but it turns out that those solutions give you somehow the leading order behavior, because there are also these nonlinear terms that will actually force solutions like that to decay slowly. So okay, and then there are other solutions which correspond to like negative eigenvalues of this operator, which decay exponentially fast. So those would be like lower order terms. Okay, and then in each of these problems, the thing that you do is just try to identify the least decaying possible solution, which does not correspond to some obvious geometric transformation. So if you look at these quadratic functions, well, the angle, so if you take the graph of the f, you're changing the angle by Laplace f to leading order. So basically, if you take two different quadratic functions on two planes, but they have the same Laplacian, then that somehow just corresponds to changing the whole angle, like just rotating the whole union as a special Lagrangian. So somehow you can kind of quotient out that behavior. And the conclusion is that the sort of least decaying interesting solution is if you have two quadratic functions with two different Laplacians. And this corresponds geometrically to rotating these two planes in a way that makes their angle not be the same. So you move from the special Lagrangian to a non-special Lagrangian configuration. So, okay, let me just write that. So the most generic possibility is sort of two quadratic polynomials. The F1, F2 on the two planes with not the same Lagrangian angle. But like the effect on the Lagrangian angle should be different on the two planes. And these are just constants for the quadratic polynomial. Okay, so let's study a little bit what this means geometrically. Okay, so what we were just describing says that we're trying to look at flows where for very large tau, they look like these two planes, and to leading order, you rotate them in this way a little bit. So there's this very nice way that you can think of, if you have a curve in C, from that you can easily generate a Lagrangian surface in C2. basically by imagining some sort of circle bundle over it. So let me just draw this picture. Probably I don't have to take up the whole time. Okay, so the thing that I drew here, this is a kind of two-dimensional slice of this W1, W2 equals epsilon. And then the two planes, so the two planes would be like, this would be, say, P1, this axis corresponds to P1, and this axis corresponds to P2. Okay, so you want to imagine that your flow looks like this, but you want to perturb it a little bit to change the angle of the two planes. And then you can imagine maybe if you make their average 0, then either you're kind of squishing them together or you're expanding them both out. It turns out that symplectically, these two things do different things, and also in terms of the flow. So it turns out that the correct thing to do is to stretch the angle a bit. So we want to make a Hamiltonian perturbation that makes it look more like this. And then here you see the point is that the closer you are to the, when epsilon is almost 0, and the closer you are to the two planes, the smaller perturbation you can make to make it look sort of stretched. So like, if you make an arbitrarily small perturbation to this curved picture, it may not have enough of a angle difference. Okay, and then so basically the non-degenerate in this case means that you look like this, that you're, yep, it's so okay, there's a little bit more background that I should have explained. So when you turn two planes into this kind of picture, this is the so-called Lagrangian connect sum. So what you want is that your surface looks like the Lagrangian connect sum with the planes stretched in this way. And then maybe I can just explain briefly what how we get this, how at least we can show that a singularity forms. Okay, so this goes actually back to Neves, and then it can be improved by this work of Lotte, Schulze, and myself. So the theorem is that if we start with this picture, I'm gonna have to write that. So a neck pinch will form if you start with the yellow picture. With this Joyce angle condition. And then let me just finish with explaining this very briefly, because this Neves's idea is very beautiful. So the idea is that suppose that you start with this kind of Lagrangian surface. So remember, it's really like a circle bundle over this. So you can imagine that there is something like that. So Neves's idea was that if the flow starts with this and it remains, it has no singularity and remains embedded, it remains embedded and smooth, then what would have to happen is that at a later time, so maybe this is your, what I call LT prime, it's perturbation of LT. What would happen is that at a later time, your flow has to look like this. That's not maybe L, D, whatever, 1. So, and the reason is that's a very nice thing in Lagrangian mean curvature flow, that there's an expanding solution that looks like this red curve. And because we stretch the angle in this way, actually at large scales, the yellow lines look like the tangent coordinate infinity of this expander. And there's some very strong stability result that if you weakly look like this expander, then at a slightly later time, you really look like the expander in a strong, smooth sense. And then what happens is that if this yellow initial condition would smoothly, in an embedded way, flow to the red one, that would be a contradiction, because actually these two yellow and red Lagrangians are not Hamiltonian isotopic. You would get a contradiction. Since this L, T prime, and L prime T1 are not. So they are smoothly isotopic, but they're not Hamiltonian isotopic, which is a quite non-trivial result in symplectic topology due to Seidel. Okay, and then you might say, well, what if it just becomes immersed? And this was Andre's original problem that he got stuck on. But it turns out that you just wait, like take this yellow initial condition, suppose that you look at the first time where it either becomes singular or immersed. But at that time, you must have a point on the flow with density at least 2. And then you can use this work up with Lotte and Schulze to prove that, well, at a large scale, it still looks like 2 transverse planes. And then that it implies that at any point where the density is 2, it still has to look like 2 transverse planes. But that cannot be the first time that you become immersed. Like if a singularity didn't form, but you just became immersed, then the first time that happens, it cannot be 2 transverse planes, because then it would also be immersed at earlier times. Okay, and then so what we show is that basically, or what I showed in this theorem 1, is that, okay, a neck pinch has to form, and then you still have this slight change in the angles, and that's exactly the thing that you need in this Joyce angle condition, that when the neck pinch forms, then you'll have 2 pieces, one corresponding to this side and the other to this side, and the angles exactly have the correct sign for this Joyce condition. Okay, so let me not, I think I'd rather just stop here, but it's a very similar picture with the 2 planes meeting along a line, that again, you want to study the linearized problem, and you come up with the sort of most generic looking non-decaying solution. And then you can show that if the leading order model, I mean, the leading term in this, like the next order term looks like that non-degenerate solution, then the flow cannot be embedded. You can somehow force some self-intersection to happen just before. And if someone is interested in that, then I could explain it later. But okay, let me stop here.